When one hears the word derivative, what would come across his mind is calculus. And in mathematics, derivative is a rate of change, and it is actually the core of calculus. Derivatives can be applied in physics in finding for the velocity might be the maximum velocity a moving object can go. It can also be applied in business in finding the marginal cost and the marginal profit. And finally, it can be applied in engineering, such as the deflection of beams and thermodynamics. So why do we need to study derivatives? Since I've mentioned earlier that derivatives is a rate of change, and and as we all know that change is constant and it is the only permanent thing in the world, we can deduce the fact that change is everywhere, and thus change derivatives rather can be applied to almost anything from slopes to time and to speed and so on. So in solving derivatives, it is important that we have a strong foundation in algebra, basic and advanced algebra, from the simple addition on what terms can we only add, the laws of logarithm and laws of exponent. We also need to have a background on trigonometry, trigonometric functions, its ratios and identities, and finally formulas. We need to have background in formulas with relation to solid geometry. So today I'm gonna share with you a problem on how to solve a derivative. So the problem I have here is that the position of an object moving along a straight line is given by s is equal to t times square root of 2t squared plus 1, wherein t is greater than or equal to 0 but less than or equal to 5, and s is measured in feet and t in seconds. So in here, we need to find the velocity and acceleration of the object after 2 seconds. So we have the equation s is equal to t times square root of 2t squared plus 1. And we know that s is the displacement since it is given that it is in feet. And we know also that displacement and its first derivative is actually the velocity of an object. And the second derivative of the displacement is actually the acceleration, or also the first derivative of the velocity. So basically what we need to find is the first derivative of s to give us the velocity and the first derivative of v to give us the acceleration. So first let us get the derivative of u and the derivative of v for easier substitution and the product rule formula. So getting the derivative of u, we will just apply the identity rule, and so we get that the derivative of u is equal to 1. For v, to get the derivative, we need to apply the power rule. We need to transform rather square root of 2t squared plus 1 into an exponent form, which would be 2t squared plus 1 raised to 1 half. And so applying the power rule, we would get the derivative of v is equal to 2t over square root of 2t squared plus 1. So using now the product rule to get the formula for velocity, we would get t times 2t over square root of 2t squared plus 1, which is the derivative of v, plus square root of 2t squared plus 1 times 1, which is the derivative of u. Okay, so this is quite long, so just pay attention on how it happened. So in this part, we can see that we got the LCD and combined two terms. So we get that the first derivative of the displacement is equal to 4t squared plus 1 all over square root of 2t squared plus 1, which is also equal to the velocity. So moving on, let's first solve for the acceleration before substituting everything. So how do we get the derivative of the velocity? First, of course, we need to apply the quotient rule, which states that v times the derivative of u minus u times the derivative of v all over v squared, wherein u is actually the numerator and v is the denominator. So in getting the derivative of u, we need to get the derivative of both terms. In this case, 4t squared is equal to 8t rather, and 1 is equal to 0 by the virtue of constant rules. So we get the derivative of u is equal to 8t. For v, like we have done earlier, we need to apply the power rule. We need to transform v into an exponent form, which will result to 2t squared plus 1 raised to 1 half. We have here that the derivative of v is 2t over square root of 2t squared plus 1. So substituting these two derivatives, u and v, to the quotient rule, we would get this. So this is the derivative of u, and this is the derivative of v. So let's just watch closely what happens. So that, and then there. And then we can see here that we have combined the two expressions in the, or the two terms rather, in the numerator. So combining further and simplifying further, we would get that this result. Oh, I'm sorry, this should actually be a negative, or a minus symbol rather, not a plus. So, okay, moving on. So there, we have this equation, and of course we need to simplify it further by multiplying the numerator by the reciprocal of the denominator. So we would get 8t cubed plus 6t all over 2t squared plus 1 raised to 1 half plus 1. Since we can see here that this is actually 1 half, and the exponent of this is 1. So combining further, we would get that the derivative of the velocity is 8t cubed plus 6t all over 2t squared plus 1 raised to 3 halves. So substituting, of course we substitute 2 to the to both formulas for velocity and acceleration. Okay, so in the velocity we can see that substituting 2, we will get 17 over 3, or 5.6 feet per second. And for the acceleration, we would get 76 over 27 is equal, is equal to 2.81 feet per second squared. This means that after 2 seconds, the velocity of the moving object is at 5.67 feet per second, while its acceleration is at 2.81 feet per second squared. So that's that. So I hope you learned something new today, and I hope that we'll see each other again on my next tutorial. Thank you for watching!